Okay, we're gonna solve the exam. One of the versions of the exam. Most are pretty similar. All of them are pretty similar, but they have different values. So if they don't correspond to what you have, don't worry about it. Just focus on the process. So first one, they're asking about the minimum design factor that will guarantee the rod will that the rod will not fail. And I know the uncertainties of my variables, and I know that it is subjected to torsion. So I know that my stress is equal to Tc over J. I know that in a circular cross section, so rod C would be half the diameter, and that the second polar moment of area would be pi over 32 times d to the fourth. So this would be 16t over pi d to the third. We've done that 1,000 times. The maximum torsion I can find due to the uncertainty would be the maximum torque, so 8% more than the normal torque, and a small diameter that is 5% smaller than my nominal diameter. So this is basically 16t1 over pi d1 cubed times 1.08 divided by 0.95 cubed, which I recognize as just 1.08 over 0.95 cubed times my nominal stress, tau. Okay, because my nominal stress was already this. And then my S min is equal to 10% less, so 0.9 my nominal strength. And I know that these two, that this cannot be higher than this. So in the critical case, these two are going to be equal. And since ND, the design factor, is defined as strength nominal over tau nominal, this would be equal to 1.08 over 0.95 cubed, which is this, or like the reciprocal of what's accompanying the maximum tau divided by 0.9. Just solving from this being equal to this. Okay, solving for S over tau, and that's 1.4. Next one, we have a steel rod OC of diameter D and yield strength 76.8, and is subjected to loads below. So I have my free body diagram. I want to design. I want to find the D for the rod to have a safety factor of safety of 3.15. Okay, so I have my free body diagram from a sum of forces in the y direction. I know that what's going up, my reaction R, has to be equal to what's going down. So the 500 going down, and 40 times 6 inches. So 240 plus 500, 740. And for my sum of moments about O, I know that my moment M naught, or M sub O, would have to be equal to the ones that are going in the opposite direction. So 500 times 8 plus this would be 8 plus 6, 14, plus half of this where this distributed load would be located, 17 times 40 times 6. So 4,080 times plus 4,880. My bending moment, my shear diagram would look like this. So my reaction 740 goes up to 740. At this point, I'm going to go down 500 to 240, and then I have a slope of 40 that coincides, because 240 at a slope of 40 for 6 inches would reach 0. I have basically this. And for my moment, so this is V, I label this properly, pounds, and this is inches. And for my bending moment, M, pounds, inches, and my X is still in inches. I would start with 8,080 and a slope of 740, and then a gentler slope, and then a curve here. So basically, and I would have to reach 0. So I know that this is going to look like this. This, then a gentle slope, and then a steep slope. Okay, and this is going to reach 0. And I don't worry about this values, because what I want to be able to calculate the d for this is the maximum moment. So this would be, oops, this would be 880. And the way I calculate this diameter is I know that my maximum stress is my over I, that my y is half the diameter, and that the I is pi over 64 d to the 4th. So basically this is a 32 m over pi d cubed, and I know that my factor of safety is s over sigma, basically s over this 32m over pi d cubed, and if I solve for d, it would be to the 1/3, so I'm solving for d, and 32m times the design factor n over s pi. If I put those numbers in, I would have that d is equal to 32 times 80 times my design factor here of 315 over s, which is this 76,800 psi times pi, and to the 1/3. Okay, and this gives me an answer of 1.5 inches. Next one, I have this structure, this pipe, and I know the external loads, the diameters, and the area. The i's and the j's and the q's are already calculated, so all I need to identify is what kind of stresses B is subjected to. So I can do a cut at where A and B are located. So it would look something like this, where B is here. I would have my z-axis, my x-axis, and my y-axis. I know that the external loads would be the same, 1200 going in the negative z direction, and I call that V because it's going to be a shear. 1500 that I'm going to call P because it's a normal load going down. Because of this force, there's going to be a moment about the x-axis, but I don't worry about that for B because B would be on the neutral axis of that bending. So this is mx, and I don't care about it. For the axis z, I would have a moment mz due to this distance of 45 times 1500 of the load, and I do worry about that because that's going to have B in compression. So I can actually already write that. Due to bending, I'm going to have a moment in this direction called mz equal to 0.45 meters times the force 1500 newtons, and that would be 67.5 newton meter. Okay, and the last one would be this distance, 90 millimeters times 1200, is going to create a moment about the y-axis, but the y-axis is the same axis as the pipe's axis, so I call that a torque. So I would have this in this direction and call the torque, and T would be equal to 0.09 meters, this 90 millimeters times this force. We'll rotate in this direction, okay? Newtons, and that is 108 newton meters. So I'm halfway done. All I need to calculate now is the stresses. So my normal stress would be P over A. P is 1500 newtons, and the area is given, the area of that ring, so 300 millimeters squared. This would just be a 5, and this is already millimeters squared, so this would be megapascals. Okay, so 5 here, and I know that because this is going down, this is a -1, sigma normal. Okay, since I already pointed out that the sigma b is going down, I'm going to calculate that, the absolute value of that. So my over I, m would be the moment about z, which is making b under compression, so 67.5 newtons. Y would be the radius, so the distance from here to here, basically 40 divided by 2, which is the diameter, so 20 millimeters, and I was given as 30,000, so 30,000 millimeters to the 4th. Now that's gonna give me a 0.045, but this is millimeters to the 4th, so that's technically just a 45 megapascals. Okay, the absolute value. Now I continue. I know that because this torque is going in this direction, I'm going to have a little vector here that will show up like this. But also because there's a force of 1200 going in that direction, there's also going to be another shear on the top part of my element B. So both are going in this direction, both the tau from shear and the tau from torsion. Okay, and I'm going to calculate those values. So tau from torsion, Tc over J, the torque is 108 Newton meters, the C is again 20 millimeters, the radius, and J is 2 times this, so 60,000 millimeters to the 4th. Now this value is going to be 36 megapascals, which would go here, or 0.036, but again, because of the units, that would be just 36 megapascals. And the tau due to shear would be VQ over IT. So V is the shear force of 1200 newtons. The Q was already calculated for me, 2500 millimeters cubed. I, the one that I've been using, millimeters to the 4th, and T would be, I didn't take any points off because I did make a mistake in the video, but T is this thickness, the actual thickness, not the diameter, just this portion here and this portion here. So basically, if I have 35 and 40 as inner and outer diameters, that is already what I need to subtract to get the thickness of 5 millimeters. Okay, so if you used 40 here, I didn't take any points off, but the correct solution would be 5 millimeters. Okay, and that gives me a value of 20 megapascals. Okay, you used 40, it would be 2.5 megapascals, and that's fine. I wouldn't take any points off of that. So this is 20, and because they're both going in the same direction, I'm going to have a 5 and 45. So sigma y would be a minus 45, and this is positive taus, again both going in the same direction, so I add them together, and that would be a 56. Sorry, 45 plus 5 is a 50. I was worried about the sign more than the value. 50, but minus because it's under compression. Okay, next one, we have a given stress element with sigma x and sigma tau xy, and a yield strength of 19 ksi. So I need these values, and I want to know if it would fail, or the factor of safety if it's assumed to be ductile or brittle materials. Okay, so my center of my Mohr circle is just the sigma average, which would be sigma x plus sigma y over 2, which would be 16. Sorry, should be 16 plus 0 over 2 equals to 8 ksi, and the radius is going to be the subtraction, so basically 8 squared plus tau xy minus 6 squared. This is one of the special triangles 3, 4, 5, so I know that this is going to be a 10 ksi. My Moore circle would look like this, where this is 8, I add 10, I subtract 10, sorry, this is an 18, and it goes from 10 to minus 10. Okay, so basically it passes through these points here, and I also know that my original states of stress state would be, not working, would be 16 and minus 6, so whatever, 16 and minus 6, and so basically the same thing, 6 and 0, so I know that it would look something like this. Okay, with my original stresses here. So this is pretty easy. If it's ductile, I have two options, since I'm only given one yield strength, would be the maximum shear stress and distortion energy, and if it's brittle, the maximum normal stress. Now, if my yield strength is 19 and my maximum stress is 18, that's what I'm going to compare for my maximum normal stress. So that would be 19 over 18, which would be 1.056. If it's shear, I will be comparing the 10 to half the yield strength of 19. So 10 is going to be greater than what the material supports. So this is going to be lower than 1, equal to 0.95. Okay, so fail, pass, fail. And distortion energy from my Moore circle, I know that sigma 1 is 18 ksi, sigma 2 is 0, and sigma 3 is minus 2 ksi here. Right. My von Mises stress would be sigma 1 minus sigma 2 squared, sigma 2 minus sigma 3 squared, and sigma 3 minus sigma 1 squared over 2 and square root of that. And this calculator, it gives me 1908 ksi. And again, this would be larger than what's allowable. What happened? Then sy, which is 19. So my factor of safety is going to be lower than 1, and it's just going to be like 995 or something. But this is also a fail. Right, now the last one. All I wanted you to do here is basically write some equations just to solve them. I didn't expect you to finish it altogether. A couple of people did do that, so that was good. So basically what I have here is a sign that has some weight, but I'm also giving you the density of the beam itself. So, and I'm asking you to use gravity. So basically you should deduce that I was hoping for you to get a distributed load from that weight of the beam. Okay, and to split the m, mass m, into 2, mg over 2 and mg over 2. Now the distance is L, L, and L. That's what the statement says here. A, B, B, C, and C, D each have a length of L. And to use Castigliano's and know the displacement at this point D, I would have to have a fake force called Q, right? So when I write my equation for that, my integral for d of d, I'm going to do a partial derivative of the energy with respect to that force Q, right? And so basically this is partial of, with respect to Q of the integral from 0 to 3L of m squared over 2ei dx. And this is, of course, integral from 0 to 3L of 2m over 2, so just m ei dm over, or partial with respect to q dx. Now, what I realize is that as I move from D to C to B to A, there's going to be some extra forces here. So basically what that's telling me is that I need to split this integral 0 to L, L to 2L, and 2L to 3L. Okay, so I'm going to have a moment 1, a moment 2, and a moment 3. All over EI, all with respect to x plus dx, and the partials of m1, m2, and m3. Okay, now this distributed load, if the weight of the bar is rho times the volume, and the volume is area times length, the weight would be times g. I know that this distributed load is basically g rho area. Okay. Now when I split this into 3, m1 and m2 and m3, it's basically just saying I need one for when my cut is between D, where my Q is, right, and my distributed load is still here, and C. If I'm standing right here, what I would see is m1 equal to, as a function of x, obviously, the opposite of this. So x times q plus the distributed load, g rho a, times x would give me the actual weight, which is located at x over 2. X over 2. Okay? And I do that for the other sections. So when I'm here, when D is here and C is here, and I have my mg over 2 and my still fake q and my distributed load here, before getting to B, at this point m2 would be qx. Now this force at x minus L, so this x minus this L, and plus the other term again, over 2. And then I don't even need to draw it, but if I do the third one, actually let's draw it. I have dc with an mg over 2, b with another mg over 2, and a cut here before reaching A. I would have my distributed load going down, my fake q, and m3 would be still q times x plus mg, no, sorry, this was an mg over 2 as well, mg over 2 at a distance of x minus L, another mg over 2 at a distance of L minus 2L, sorry, of x minus 2L, and the distributed load, which hasn't changed. Okay, now what I would need is just the derivative of this with respect to q. This is just an x. Same here. And same here. And to put that all in these integrals, which are pretty straightforward. Again, even if you stated this and you did like a 1 or 2 free body diagrams for the different cuts, that would be enough. But a lot of people didn't notice this, or didn't notice that it had to be split into 3 integrals. You can change the limits to if you state it as a different equation, or like if you use different equations for the moment. But basically those two things, like even just drawing a free body diagram, acknowledging that there's a distributed load, and knowing that you're gonna have a fake load q to be able to calculate that displacement at D, Was enough.